Hello, everybody. Today is our second lesson in the series, which I planned for demonstration of capabilities of the IQmol program in combination with calculation using the Q-Chem computational engine. So today we'll be talking about molecular vibrations. Each molecule in general has 6 degrees of freedom as total, 3 rotational and 3 vibrational if it's not linear molecule, and their corresponding number of vibration depending on the number of atoms. So let me share the screen and show you something about molecular vibration. Okay, so first of all, the vibration depending on the type could be stretching the bonds, bending the, changing the angles, which is called bending or deformation vibration, and also torsion when 2 groups rotate around one bond. So since their vibrations are also belong to electromagnetic wave types, their energy is laying down between visible light and microwave. So with bond lengths roughly between 75 nanometer and 1 millimeter, it's between 40 terahertz and 30 gigahertz, 300 gigahertz. And energetically, it's between 17 eV and 124 milli-electron volt, which corresponds roughly 40 kilocalories per mole, range between 40 kilocalories and 30 calories. So when we form the simple molecule from 2 atoms, each atom has 3 degrees of freedom, translational in each direction in our 3-dimensional world. So when we combine them together, we form one bond, and we'll have 1 stretching vibrations, and the remaining degrees of freedom, 5 would correspond to 3 translational mode and 2 rotational mode. 1 rotational mode for linear molecules would not exist because there is no momentum along the axis. So for 3 atomic molecule, depending on whether it's linear or non-linear, we either will have 4 degrees of freedom, 4 degrees for vibrations, or 3 vibration for linear and 3 vibration for non-linear molecule. The last example is for 4 atomic molecule, total degrees of freedom 12, and we subtract the 6 degrees of freedom for molecule moving as a total, rotational and translational, and we get 6 vibrational mode, which correspond 3 stretching for each, 1 for each bond, and 2 bending for these 2 angles, and 1 torsional along this middle bond. So the general formula for the number of vibrational mode is 3n minus 6 and number of atoms for nonlinear, and 3n minus 5 for linear molecule. The example of a molecule which I'll show you today would be methanol. So methanol has 6 atoms, so which correspond to a total 18 degrees of freedom, subtracting 6 for molecule as total, and we'll get 12 vibrational, 5 stretching for all this bond, 1, 2, 3 CH, 1 C oxygen, and 1 OH, and one torsional along the CO bond, and 6 bending vibration. So let me just stop share and go and open the screen for IQmol. Okay, so first of all, let's us build the methanol molecules. So I go and select carbon, click, add hydrogens. Okay, so now I will go and convert 1 hydrogen into the oxygen. If I click again on add hydrogen, so we'll add hydrogen on the molecule. So now we get methanol molecule. So let's go then optimize it with molecular mechanics. prior doing quantum mechanical calculation. And now the next step, so we prepare the jobs for doing frequency calculation. In order to do this, we click on calculation, go to Q-Chem setup. So I will use their default method, which is Hunter-Fock with 631G basis set. And the first job should be optimizing their geometry. So first job will be geometry. And when geometry is optimized, on optimized geometry, we will need to do the frequency calculation. So the second job would be frequencies. Okay, so and now I submit the job at the computer center in California. Click on submit. Okay, I need to give a title for the job. Let's call it CH3OH and submit. Okay, let's see how long it will take. If it takes somewhat longer, so I would show you the previously done calculation, but hopefully it would not be too long to see. It depends on how their computer is busy. Okay, usually it takes just a few seconds. So while its job is doing, okay, it's already done. So and now it's asking, do I want to copy result from the server? Of course, I click on yes. So now I have to select the folder where I want to save the result. So there would be CH3OH. So I select the folder, and okay, there is some error. Okay, so hopefully doesn't impact our result. Okay, so now I click on this error. So, and I need to select here the frequency, and now I have a different set of frequency. So let's start from the lowest one. The numbers are given in so-called Wave numbers in centimeters power -1. So if they multiply by speed of light, so they would correspond then the frequencies. So the lowest frequency, if I double click on it, it should show you the vibration. Okay, you can let me just increase it so you will see. Okay, so you can easily see that it is torsional vibration. So OH group and CH3 along the CO bond. So the next bond is, you can see that's a stretching bond. So the previous one was torsional. This is stretching bond, CO. Okay, so let's go now back to the strongest bond. So there are the strongest bond and the highest frequency correspond to OH vibration. So, and then the next one is CH. There should be three CH vibrations. So, and they're in a similar energy. So this is okay, let me just rotate it. Now that's unsymmetric. So this one is symmetric CH bond. And so our remaining the bending bond of different kind. Let's quickly watch all of them. Okay, all right. So this is a different bending bonds of the methanol. So now if you go and click on the frequency, we will see the spectrum. So the height is show the intensity of the bond, and the position is the energy of bond. If you want to see the real spectrum, which would be broadened by temperature, so we can see their spectrum of their infrared spectrum of the molecule. Its vibration. It's like a fingerprint of the molecules. Okay, so this resume our lesson about vibration using the IQmol and program in combination with Q-Chem calculations. Thank you so much.